SwayamPrabha. Digital India. Educated India.
Hello everyone. In today's lecture, we'll be looking at where does surface tension come from and what is its connection to interfacial energy. Now we have to remember that in the previous lecture, we have looked at the pressure jump across an interface in the absence of surface tension. The next thing that we want to do is to understand what is the pressure jump across an interface in the presence of surface tension. But before we do that, we want to understand what is surface tension, where does it come from, and what's its connection to interfacial energy. Now, a student in fluid dynamics could ignore this particular lecture and just say that surface tension is a real thing for me and I don't have to worry about where it's coming from as long as it exists and I can proceed with that. That's one approach to take. But another approach to take is to ask, what is the connection between surface tension, the fluid dynamics and thermodynamics, right? Because surface tension ultimately is a thermodynamic idea. It comes from there, and we have to understand, if you want to understand where does it come from, then we have to look at understand a little bit of thermodynamics. One of the things that we know about surface tension is it's a short range force, right? And it has, even though it's a short range force, it actually has long range effects. Okay, so let me just write that down. It's a short range effect. Can have macroscopic consequences, and I can give you a bunch of examples. For example, here I'm showing you 3 examples. The capillary rise in a tube is basically, to understand this, we need to understand that it's basically between the interactions of the solid, the capillary tube, and the fluid gas interface, right? And these interactions lead to a macroscopic effect. It could be the Rayleigh-Plateau instability shown schematically, where a liquid jet basically breaks up into droplets, or how a droplet, a sessile drop, interacts with the solid surface. Okay, all these 3 examples that I'm showing you are macroscopic features that we can see with our naked eye. Yet, their origins are from surface tension. And therefore, it's an interesting way that you can have a short range force and still have a macroscopic effect. Now, there is one disclaimer sort of I want to put out here, which is that I will basically only go look at these topics, the origins of surface tension and the connection to intermolecular forces, in a very simplistic way. I will be sacrificing quite a bit of rigor in the hope that it will lend some clarity to the subject. But there are several excellent original sources that a student can consult, and most of the topics that I'm going to talk about today are based on these excellent sources. Israel Chwili's book on intermolecular and surface forces is a seminal book on this topic. The molecular origin of surface tension was first looked at by Sir Michael Berry. And then there's a more recent paper about just over 10 years ago, which was revisited this problem and asked the connection between surface tension and contact angles as well. Okay, so a student, these books and papers are very easily available, and a student who wants to go deeper into the subject can actually consult these sources. Now let's start with asking, what is the nature of molecular interactions? Okay, now to understand this, I am basically showing you two simple diagrams here. We want to understand molecular interactions. Let's consider a mixture of 2 kinds of molecules, and in the first state they are in a dispersed state, as I've called it here. Now, in the dispersed state, the molecules A shown in blue and the molecules B shown in orange, they basically coexist together. And in this particular case of taken the number of molecules to be the same, and you can see that there are bonds between A and A as well as A and B, and in some cases we have bonds between B and B as well, right? Now we can go from this dispersed state where the mixture is molecules are completely mixed together to a state which is what Israel actually calls it as an associated state, where now you have a lot more cluster of there's a cluster of A molecules and a cluster of B molecules. Now to go from the dispersed state to an associated state, there has to be a change in the energy. Okay, and this change in energy is directly connected to the binding energy of molecule A with A or molecule A with B. For example, let me highlight one particular case. So for example, these two molecules, which I'm highlighting in yellow in the dispersed phase. Now there's a binding energy between A and B. Now I have gone from that state to a state where I have two molecules A and A. Therefore, if I know the total number of molecules that have changed in this from going from one state to another, then if I know how the configuration has changed, then I can estimate what is the change in the energy or change in the free energy, to be more precise. Okay, so I can write down what is the binding energy. So the binding energy would be of molecules A and B in contact can be written as, so let's look at AA. The binding energy, I'm simply writing it as minus A square. And similarly, the binding energy with BB is minus B square. And binding energy of AB would be minus AB. So you can think of A and B are as quantities which are proportional to some more fundamental quantity. For example, if these are charged molecules, A could be proportional to the amount of charge that is present, correct? So this is even true for even gravitational systems, where A and B could be thought of as associated with the mass of the, so that the interaction energy would be proportional to the product of the masses. Okay. Now we are looking at a more microscopic picture, which are mostly Coulombic interactions. Now we were having written down the binding energy of A with A and B with B and so on. We can write down the binding energies for different configurations. So now I can ask, what is the change in the state going from the dispersed state to an associated state? So let's look at that a bit more closely. So let's consider a system of these two states. Now, if I basically go from, let's say, the change in the energy, this delta W that I've written down here, this would be the difference between the associated state, the energy of the associated state, minus the energy of the dissociated state. Okay. This is the difference in the energy. Now I can write down the difference in the energy as how many neighbors have switched around. Let's say there is n number of neighbors have switched. Therefore, I have A minus B whole square, where n is the number of bonds as such that have been formed in the process of association. New bonds that have been formed in the process of association, and some bonds which have been removed in the process of association. Okay. Now we can simplify this analysis with expression. Okay, where I can now say this is n is A square plus B square minus 2AB. Okay. But let's remember WAA is minus A square, WBB is minus B square, correct? So A minus B whole square can also be written as this quantity here. If I were to write it in red, this can also be written as square root of minus WAA times square root of minus WBB whole square, right? So this expression here that I have here can also be written as N times WAA plus WBB minus 2 times WAB. So we have this associated state. When we go from one state to another state, the associated state is associated with the change in the energy of the nets of the state of this configuration. And I can write it down in terms of individual binding energies. Right? Now, why are we looking at this? Because once we have this general idea that it's basically associated with how individual interactions can lead to an interaction of a cluster. Okay. Now I want to take it one step further and expand it to surfaces. So let's look at interaction at surfaces. Okay. Now to understand the interaction of surfaces, let's basically start by looking at one simple cartoon. Okay. So here what I'm showing you is there are two surfaces, A and A, embedded in another medium B. So these could be two solids or two liquids of A in another medium B. Okay, we'll think of all these examples in the context of liquids, though several of these ideas also carry over easily to solids. Now let's look at this particular case that I've shown here. So I have AA shown in orange, okay, embedded in B. Now notice that when I go from a configuration on the left to a configuration on the right, I have basically joined AA. In other words, I have eliminated two surfaces of AB. Okay, if I were to highlight those two surfaces, if I were to highlight them, it is basically one surface here and another surface here. These two surfaces that I'm highlighting have disappeared. And as a result, the change in the energy, the change in the free energy going from one state to another state would be -2 of gamma AB. And again, the factor 2 is coming because I have two surfaces have been eliminated. Okay. This is the change. So let me write this down. This is worth writing this down. The change in the free energy in this case, it is negative of bringing these two surfaces together by -2 gamma AB. Okay. This quantity delta W is twice the interfacial energy, okay, of the interface AB. Okay. Now let's consider another situation where I'm looking at two surfaces in the two different surfaces A and B, okay, in vacuum. Okay, so this is the kind of picture that I have. Okay, so I have two surfaces A and B. So this is nothing but interaction of two surfaces in vacuum. Okay, so if there are n bonds per unit area, then change associated bringing A and B into contact. Okay, this is all these ideas are per unit area into contact. This change would be n times WAB. Okay, this is basically this quantity delta W that we've written down. This is the work of addition or the addition energy. Okay, now I can take the same idea forward and say instead of basically interaction between bringing two surfaces of different materials together, let's say if I'm bringing two surfaces of the same material together, okay, for example, as shown in this cartoon here, I have A and A coming together. In this particular case, the total work that a change in energy is associated with what is called as the work of cohesion. So let me write that down. The energy change associated with bringing two unit areas of A into contact with each other in vacuum. Vacuum is called the cohesion energy or the work of cohesion. And in this particular case, the work of cohesion gamma A would be, there's a reduction in the surface. Okay, I have eliminated the two surfaces here. Okay, and therefore I have joined them with one surface, and that's where the factor half comes in. Okay, and n is the number of bonds per unit area. Okay, in some cases, in some books, you'll also see gamma A could also be equally written as gamma AV, where V stands for vacuum. Okay, so now what we have is we have the work of addition and we have the work of cohesion. Right? Now let's look at interaction energy. We've looked at a couple of quantities, different quantities here. We've looked at binding energy. Let me take that back. We have the binding energy between molecules. We have binding energy between molecules. Then we have the so-called surface energy. We have the work of addition. We have the work of cohesion. And now we look at interfacial energy. The interfacial energy, I'll write it as gamma AB. It's something that we saw in the first diagram. It is half n of A minus B whole square. Okay. This quantity, interfacial energy, we have to remember that this is very different from the work of addition. The work of addition, you can say, is WAB is minus NAB. Okay. This is very different from the work of addition. Okay. Now this gamma AB that I have here can now be written as gamma A plus gamma B. This is just an expansion of this A minus B whole square that we had seen, minus WAB. This is per unit area. Okay. I would like all of you to work it out yourself. We already have A minus B whole square that we have written down earlier. A square would be associated with gamma A. B square was associated with gamma B. Okay. And WAB is the work of addition. Okay. So, so now you can have also another way to write, or if I were to more explicitly write it, is gamma A plus gamma B minus delta gamma A. And this quantity here is the work of addition. Okay. So it's important to remember that this work of addition that we have, the interfacial energy that we have here, is related to the extra energy, extra surface that we are creating, right? So let me write that down. The interfacial energy is related to the extra surface energy that is either being created or eliminated. In the process of separating. If I'm separating two surfaces, I'm creating an extra new surface between A and B. Or if I'm eliminating surface, which means I'm joining, let's say, A and A in the presence of B, then I can say it as joining. In the process of separating or joining, the interfacial energy is directly related to the extra surface energy that is either being created or eliminated in the process of separating or joining in the presence of another medium. Okay. So we can also relate it to the work of cohesion that we wrote down. So if I write down, I know that gamma A is directly connected to the work of cohesion. So WA by 2, WB by 2, that will be the work of cohesion minus the change because of the change in energy, free energy because of the work of addition. Okay. So this is a very quick and a short introduction to the thermodynamic origins of interfacial energy and surface tension. Okay. But I want to also look at another very important aspect, which is the mechanistic view of surface tension and interfacial energy. We'll look at surface tension. The same ideas carry over to interfacial energy or interfacial tension as well. Okay. So surprisingly, even though surface tension, the ideas of surface tension, interfacial energies have been around for a long time, well over 200 years ago, it's only in the 1970s that the molecular origin of surface tension was closely looked at. Okay, and this goes back to the work of Sir Michael Berry in 1971. Okay, so the question that we are interested in asking is, let me separate this out. The question that we are interested in asking, what is the molecular origin of surface tension? Okay. Now, the common explanation that is given to us is that this is shown schematically in this drawing, that in most textbooks you will find this explanation, and I'm borrowing several of these ideas and schematics drawings from Sir Michael Berry's paper and other papers. So here is an interface, okay, and in the liquid, what you have is the interpretation that is commonly told is that there are these molecules of the liquid which basically are equally attracted to their neighbors. And because the liquid as a whole is not moving in a static state, there is equilibrium. And therefore, a molecule in the bulk shown with red arrows is equally being pulled in all directions, and there is an equilibrium. Whereas a molecule at the surface basically does not have enough neighbors. Correct? This is the kind of interpretation that is normally given for surface energy. Okay, but there is a fallacy with this, or a flaw with this idea, and I'll tell you what is the main flaw with this idea. Okay, the first flaw with this idea is that the molecules are not static. Okay, right? That's the first flaw, that the molecules are not static. What is the second flaw with the idea? This explanation does not tell us why is the force tangential to the interface or parallel to the interface. Okay, let me write this down more clearly. So if I look at the blue arrows for a molecule that is near the interface, okay, this of course this drawing is highly simplistic. Okay, but it hopefully stimulates some thought in all of you. If you look at the blue molecule, it gives the impression that the resultant force is downward, and this gives you the impression that the resultant force is 0. Straight away, this leads to a dilemma. If the resultant force is downwards, But why is surface tension a force parallel to the interface? There are several examples that we can do to confirm this, that the surface tension force is indeed a force parallel to the interface. We'll also see some demonstrations in the form of videos. So let's try and understand how do we explain this. Again, I will be sacrificing quite a bit of rigor, and I would urge the students to look at the original sources. Okay, but let's start with what is the nature of interactions between surfaces. Okay, the nature of interaction between surfaces can be simplistically shown like this. In this case, you can think of something like a Lennard-Jones potential. Okay, but this is a interaction potential is being shown as a function of separating resistance between the molecules. Okay, so you have two molecules here. Okay, separated by distance r. Okay, so when the molecules come fairly close to each other, okay, then there is a very strong repulsion. It's almost like a hard sphere repulsion. Okay, whereas as you go further away, there is a long range attraction which will persist for a very long distance. Okay. Now we can put in numbers here. If we take in the Lennard-Jones potential, we can quantify this graph more precisely. But that's not my goal. Okay. But I want you to keep this picture that repulsion forces are very short range, whereas attractive forces are sort of slightly longer range. Okay. So let me write that down. It's worth writing this down. Repulsion forces, very short range. And it's important to understand that when we use the word short range and long range, we're really we're comparing the sizes to the molecular dimensions. Okay, the sizes of the molecules themselves. Okay, so repulsion forces are really happen when molecules are basically come to distances which are comparable to their own size, whereas attraction force can be felt over several molecular distances. Okay, one should not confuse this short and long range, these words of short and long, in any macroscopic sense. These are all microscopic. These words are being used in a microscopic sense. Okay. So this idea of repulsion and being short range immediately leads us to an interesting conclusion. Repulsion forces are largely isotropic. Okay, isotropic. And it's important to understand that isotropic even at an interface. Okay, and attractive forces are exhibit strong anisotropy as one approaches the interface. Okay. Now, why is this the case? The reason this is the case is because if you think about what is repulsion is going to be experienced because of the push from surrounding molecules, right? But attraction forces are in the same way, but they're because of the pull of the surrounding molecules. But then, because attraction forces are slightly longer range forces, when one comes close to the interface, the number of molecules in the neighborhood matter for attractive forces, but not so much for repulsion forces. So, in other words, I can whatever I've said in words, I can write this down as repulsion forces crucially are insensitive to the local molecular arrangement Okay, maybe a better word to use is, rather than insensitive, a better word to use would be less sensitive, far less sensitive, okay, to the local molecular arrangement, whereas attractive forces are sensitive to the molecular arrangement in the neighborhood. So therefore, I can now extend this to a drawing that I saw in Marchand et al. I gave the reference at the top of this lecture. So let's consider a liquid gas interface. One could also think about a liquid vapor interface. Now the impression that we get is from this idea is that let's consider the situation in the bulk. Okay, if you have a molecule in the bulk, the attraction forces are shown in black arrows, and therefore they're being pulled. Every molecule is being pulled equally in all directions. And remember, all of these are equilibrium ideas. Whereas repulsion, on the other hand, shown with red arrows, basically point inwards. Okay. Now, in the bulk, these two are in balance, and therefore an equilibrium is established. Correct? The net forces are balanced, and more importantly, the sizes of the arrows are also of the same size. Okay. Now, as we take this molecule and go towards the interface, the number of molecules in the neighborhood change. More particularly, if you look at the attraction forces, they become smaller. The size of the arrow is a measure of the magnitude of the force. Okay. The number of molecules below this particular molecule is high, but above it, we have very few liquid molecules, and therefore it matters to the attractive force. So attractive force basically it does not diminishes in the bottom direction, but it remains substantial. Attraction forces remain in the horizontal direction. On the other hand, repulsion forces, because of the number of neighbors have decreased, it is largely isotropic in nature. The magnitude of repulsion has also decreased, but because of its isotropic nature, it's basically the same in all directions. And so what then comes out of this kind of a mechanistic picture that we have created here is that there is a net tangential attraction force. Okay, net tangential attraction force at the interface. This is exactly the molecular origin of surface tension. This is a mechanistic view of where surface tension is coming from. Okay. We can also look at the same idea in a different way that is discussed at length in Sir Michael Berry's paper. So let's look at an image like this. This is what we are trying to look at is the forces on a square. Okay, it could be in 3 dimensions, it could be a cube element. Okay, so before I discuss this diagram, let's first look at what is basically pressure. Okay, so if I have an interface here, I can basically this is a liquid gas interface. I can basically ask what is the force, what is pressure in a liquid. The pressure in a liquid, to understand this, what we could do is we could take a test section which is, let's say, horizontal or vertical or any orientation. Now, if you are away in the bulk, these are basically the number of interactions on either side of this test section. These are test surfaces or test surfaces. Okay. Now, these two surfaces, the orientation I've shown one to be vertical, one to be horizontal. There is a good reason for it. I've drawn the interface to be largely horizontal, the liquid gas interface. But when you're in the bulk, the orientation of the test surface does not matter. Okay, because you have a large number of molecules on all sides of this test section, there is isotropy, and therefore the pressure itself will eventually turn out to be an isotropic quantity. Okay, in the bulk. Now let's look at what happens as you take these test surfaces to the interface. Okay, if you go near the interface, and because I'll deliberately draw it slightly small and short. So I have two test surfaces here. Okay. Now there are two kinds of interactions that happen. There could be a test surface here in this particular case. The test surface, let's say look at the test surface which is vertical. Okay. If it's vertical, the force you have, we will refer to it as P tangent. Okay. Whereas if the test surface is horizontal, meaning its normal vector is perpendicular to the surface, normal vector is normal to the interface, we refer to the pressure as Pm and ask what is the direction of this Pm. Now we will take this idea, first look at the bulk. Okay, now we'll combine both these test surfaces and come up with one single fluid element. Let's consider a case of a square element in 2D, or it could be a cube in 3D. Okay. Now, if you're in the bulk, the orientation does not matter of the test surface. So a vertical surface and a horizontal surface experience the same force, and this is what we refer to as pressure. If you're going far away from the interface, then there could be gravitational effects, but I'm currently ignoring those ideas, the idea of changes in pressure because of gravity, because we are looking at what is happening near a surface. So gravitational effects can be ignored. We'll examine the effect of gravity later. Now, when you come close to the surface, this pressure being equal in all directions does not work. And I've shown this schematically here. So we start with the bulk. This is in the bulk. You're again in the bulk here, but in the gas phase. Okay. Now, Pn is basically because of repulsion. Okay. Pt is dominated by attraction. There's a longer range attraction in the horizontal. Okay. Whereas there is a short range repulsion in the vertical. Okay. And therefore, when you come close to an interface, Pt is much larger than Pn. And this will manifest as a net attractive force. One should not forget that the system is still in equilibrium. Okay, even though there is a net attractive force that has emerged at the surface, the system is still in equilibrium because the total amount of force on this element that we're taking is perfectly getting cancelled. So there is no unbalanced force, and as a result, if you were to look at a small element, it will not spontaneously move to the left or the right in this diagram. Okay, so this is fundamentally the origin of how surface tension will manifest at a macroscopic scale as a tension force. Now the next step that we want to do is to extend this to jump conditions. Okay, which is exactly what we'll be looking at in the next lecture. But there's another fact that I want to look at, which is how to measure surface tension as well. How does one actually measure these surface tension forces? And we will have a separate lecture on common measurement techniques for surface tension, but that will be in another lecture.